Hi everyone, hope the audio is clear. All right, so today we're going to talk about strings. And before we start, a bit about myself. My name is Omer, that's my Twitter handle. I am an iOS developer at C. You might have seen our booth outside. So, strings, right? Seems quite straightforward. I'm going to tell you guys a story first of how this talk title came about. So, I was in Thailand over a few weeks ago when Sub messaged me and asked me, hey, what's the title you want to set for this talk? And I thought, hey, my talk is about strings, so yeah, strings and Swift sounds good, right? But I was in Thailand, and the Thai language, if you know, the Thai writing system is highly decorated by several diacritics. There's several markings. They look quite beautiful. They look quite fun. So I decided, hey, let's make this a bit more fun, and let's encode my title using a new language called Funglish, which is English, but with diacritics, right? So it looks a lot more fun. And I thought this would be a good test to see how Sub's website and Sub's app will handle my talk title. And as it turns out, I did see some problems. So that is the iOS Conf website. As you can see, my title was not rendered correctly. And sadly, on the iOS app, they didn't even render my title. That's not my title. My title is not strings. That's English. I was writing in Funglish. It's a different language. Anyways, the point I'm trying to derive here is that strings are actually quite hard. They are not easy, and that's going to be my main takeaway in this talk. So, let's begin. And throughout this talk, I'm going to look at this string. So if we have this string here, we love mobile phones. Actually, the rendering is a bit screwed up. That's a purple heart, and that's actually meant to be an iPhone. But forget that, this is Unicode. And the V is with an accent. It's for a reason. But anyway, just memorize the string, okay? So there's a few questions that come about whenever we talk about strings. Questions like, what is the length of this string? Some of you might think it's 4. Some might think it's 5. I'll get to that later. What happens if I remove the character at index 1? What's the result of the string I'm going to get? And what does this string look like in bytes, right? And what is the complexity for common operations like insertion, appending, removal, etc.? So, first of all, like any major question, we're going to have a philosophical debate, and we're going to resolve this philosophical debate using the best means possible, which is violence, obviously. So this great philosophical debate started in the golden era of C, where everything is an array of bytes. There's no such thing as string. You don't need a string. It's just an array of bytes, right? And then you had slightly more mature languages come about who said, no, it's not an array of bytes. It's an array of code points. And then you have some even more mature languages these days, like Swift, that come about, no, it's actually something called grapheme clusters, which sounds like a sci-fi weapon, right? And then you have some other languages like Python 3, which will say, no, it's UTF-8. And there's some other languages that say, no, it's UTF-16. What do all these terms mean? And that is something that we'll look at in this talk, okay? So, like any philosophical discussion, let's go in a bit of history. And our history begins with the Cold War, all right? So during the Cold War, we had this thing called ASCII. Everyone loves ASCII, right? ASCII is great. 7 bits, that's all you ever need. American Standard for Information Interchange, yes. All right? 7 bits though. When microprocessors started taking off, they were 8 bits, right? So what do we do with that 8 bit? And that's when the Soviets come in. All right? Comrade, let me help you with that 8 bit. So, the Soviets decided, hey, screw you, our language is not going to, Cyrillic isn't going to fit in your stupid 7-bit system, and I'm going to design my code page, this thing called a code page, it's K018R, to specify how to encode the remaining 8-bit and map them onto Cyrillic characters. And naturally, you can see there's not a very scalable solution if every single language starts doing this, right? It's not very scalable. So, at the end of the Cold War, as it so happens, we have something called Unicode, similar to the UN, but slightly more successful. What Unicode did is actually quite straightforward, very, very simple. In 1987, Unicode is a standard that's managed by the Unicode Consortium, similar to the United Nations Security Council. And very simple thing they do is they just assign a unique number called a code point to every letter in every language. That's all. Actually, that's it. That's all they do. Nothing else. That's all those buggers do all day long. They just look at, they say, okay, smiley face, you are 0x, xx, blah, blah, blah. So, let me show you that string again. This is that string I mentioned earlier, and these are the Unicode points. They're in hex, all right? And each Unicode point also has a name. So the heart is called a purple heart. I don't know, for some reason when I render it in the presentation mode, it renders as black and white. This is a bug on Google Slides. Someone from Google, please report this for me. All right. Okay, but here's the problem, right? Unicode just specified the code point. How do you implement this? Or how do you encode it? Meh, not our problem. So they are pretty similar to the UN, right? Anyways, so encoding is not their problem. And how do we fix it? How do we do encoding at the end? And there's a few complex problems here actually. It's not that straightforward. So Unicode 9.0 contains 128,000 characters. And we cannot even fit these in 8 bits, let alone 16 bits. We actually need 17 bits to fit them. And the max capability actually for Unicode is 21 bits. So here's an idea. Why don't we use 32 bits for each character, right? Sounds good. They'll fit everything in nicely. But it's super space inefficient, right? Let's say you're only dealing with ASCII content, or you're only dealing with stupid languages like English, which only have 26 letters. Well, you're going to take 4x the amount of space, which is pretty bad, even though we have pretty high memory phones these days. And the problem is that it's not backwards compatible with a lot of existing protocols that rely on ASCII or ASCII-based systems. So we have a problem here. And that is where this thing comes in, UTF-8. So UTF-8 is a character encoding that is massively popular these days, and within the last few years it's shot up in popularity. And it's actually this idea behind it is very simple. So it's a character encoding that is capable of representing all possible Unicode points, all 21 bits. And the way it does it is it uses a variable length encoding. So it will use 8-bit code units, okay? And it's backwards compatible with ASCII, and it'll use 1 to 4 bytes to represent those 21 bits that we need to represent our Unicode point. And I'll just give you guys a brief idea of how it works. So this is something I copied off Wikipedia. And the basic idea here is that you just need to look at the first bit of your first byte. If the first bit is 0, means there's only 1 byte. If the first bit is 110, means you actually have 2 bytes. If the first bit is 1110, you have 3 bytes. 4110, you have 4 bytes. So the length of the number of ones will give you what is the number of bytes, basically, that you need. And every secondary byte will be preceded with 10. 10 just means that this thing is a continuation. So the nice thing about encoding it this way is if you have any sequence of UTF-8, you can tell whether it is a starting byte or whether it's in the middle of some sequence. So this thing is called self-synchronizing. It's quite powerful for a Unicode, for encoding format. So I'm just going to show you the Unicode. You guys don't need to worry about it for our characters. Just the main thing to bear in mind is that it's variable length. So the W character takes 1 byte. The E with the accent takes 2 bytes, the heart takes 4 bytes, and the mobile phone also takes 4 bytes, okay? So if you calculate the number of bytes, it's not 4. The total number of bytes is 11. All right, here's another question, complexity. How long does it take for you to index a code point? Let's say I want to, I have a UTF-8 encoded string, and I want to find what is the string, what is my character at this index? It's actually not an O1 operation. It's actually an ON operation because you have to go through the string to find out, because it's variable length, you need to find out what's the what it's composed of, and therefore you need to do some analysis on it. Similarly, calculating the length is also ON. And the nice thing about it is that it's pretty space efficient compared to UTF-16 and UTF-32, two other encoding formats that I'm not going to talk about today. And the best part about UTF-8 is that it's compatible with ASCII, because the first byte, the 7 bits, remain the same. Okay? So now that we understand UTF-8, we're pretty good to go, right? We can pretty much understand most of strings, and we should all just use UTF-8, and UTF-8 will solve all our problems. No. So now I'm going to talk about the sci-fi weapon I mentioned earlier, the grapheme clusters. So what are grapheme clusters? So remember I mentioned the E with the accent? Actually, in Unicode, there's two ways to represent it. One way is to just use the Unicode code point for it, which is Latin small e with the acute. Another way to represent the same thing, actually, is to use two characters, two Unicode points, which when combined will render as that, E with the accent. So you can use the Latin small e and you can use this combining acute accent, which is a separate code point. And combining them both will give you this letter. And this is called a diacritic. So let's say we use the second method, right, to encode our string that we mentioned before. So now we have W, E, accent, heart, and mobile phone. How many characters are there? Are these 5 characters or 4 characters? Well, it depends, right? And this is where the concept of grapheme clusters comes in. A grapheme cluster is essentially the smallest unit a human reader would consider a character. And removing a grapheme cluster will give you something that's human readable. And the problem is no single number of bytes or code points can describe a grapheme cluster, because your grapheme cluster can be composed of a lot of code points. This is a simple case where I just have 2 code points and I compose into this grapheme cluster. So to do this clustering, right, there obviously has to be some standard. Like, you can't just let people go wild like you did in the days of the Cold War, right? So actually, Unicode has a standard for doing this. And the process by which they do this is called normalization. So in many writing systems, a single character, like I mentioned, can be composed of a base letter plus an accent or some other decoration. And because there's so many combinations of these, it's just not possible for Unicode to represent all of them as code points. It just won't be possible, and we'll run out of space, or we might need 100 or 200-bit integers to store them. For compatibility reasons, actually Unicode does have single code points for several common combinations, like E with the accent, like I mentioned earlier. And we need to apply this normalization transform to perform simple operations like equality. For example, if I'm using the E plus acute accent and I compare that to the single Unicode character, they're actually both the same, graphically speaking. So I should actually handle that, right? And Unicode specifies a lot of these cases in the standard. If there are people who love reading standards, and there are some people I believe who do, who enjoy this and take this for their toilet reading, just go to this link. You'll enjoy it quite a bit. There's a lot of rules there. I won't dig into the rules. Okay, so now that we've dealt with grapheme clusters, now you'll understand why I was not very happy with the iOS Conf not using my correct topic. Actually, my strings is also 7 grapheme clusters, just like the original strings. It's just that I have a lot of diacritics around it that I'm actually abusing from several languages. So, but the point is that both of these are actually 7 characters in the human readable sense. All right, now that we understand grapheme clusters, we should be done, right? But not yet, not so fast. There's another concept of strings that is particularly interesting, which is bidirectional text. I don't know why, but for some reason, human beings have decided that writing systems should start from left to right and right to left. And they didn't seem to standardize it. So we have many languages that actually go from left to right, and many that go from right to left, particularly Arabic, my own language called Urdu. So how does Unicode handle bidirectional text? Well, actually what happens is every code point in Unicode has a directionality assigned to it along with a strength, okay? So this will tell the renderer how to order this code point when you are displaying it, whether it's left to right or right to left. And actually in terms of the data, this might seem a bit confusing, but in terms of data, the right to left text is actually represented in the same order as the left to right text. So when you look at the data, you'll see, how does it look like that? Let me show you an example. And one more thing to note is the first character in the sequence will determine the document direction. So here's some examples of some strong direction characters. Characters like ABC, which are strong left to right characters, and characters like alif, te, be, these Arabic characters, which are strong right to left characters. And these will be rendered in their intrinsic directions regardless of the document direction. We also have weak direction characters. These characters will just use the direction they are embedded in, and this creates a lot of funny use cases. And they have some direction when they appear alone, but when embedded in strong, they will actually use the strong. And there's some very complex algorithms to align them when render time. And they won't create a directional boundary, it's called. So here's an example of all this, right? Let's say I have this string where I have this left to right English text, and then I have some Arabic right to left text, and then I continue with some left to right text, all right? The interesting thing I want you to highlight here is that in the encoding, the ordering of the right to left is still left to right, which I know sounds pretty confusing, but that's the main thing I want to highlight, that when you encode it, the ordering is all in one direction, but when you render it, it'll be the other direction, okay? And like usually for most people who do localization, this may not matter that much because you don't care about poor Arab countries. But in case you do, and we do in our company, so we have this interesting scenario where let's say we're rendering a place where you enter your mobile phone number, and like any good app, we want to pre-fill the country code, right? So we have this formatted string where we want to show the country code first, followed by the country name. And we use this simple piece of Swift code, right? We have the percentage at, this part will fill the country phone code, and this part will fill the country name. But in English, when we render it, it works great. So +65 Singapore. However, if I use Arabic, this is Singapore for Arabic, in Arabic, it'll actually render the other way around. And this is because the bracket is a neutral directional character, and numbers are weak direction, so they actually don't impose any direction. And the direction is only imposed by the Arabic characters, which have a strong direction. And this caused my UI to screw up, naturally. I don't want it to look like this, right? So how do I fix this? Right, this is quite a hard problem to fix, it seems. Turns out the geeks at Unicode did figure this out. They predicted this problem. And they provide this thing called direction markers. And direction markers are zero-width characters that basically allow you to induce directionality. So for example, this character, U200E, is a left to right direction marker. And if I add this character, what it will do is it'll basically force the direction to be left to right, making my string render correctly. So these are tricks that you should be aware of if you are dealing with right to left, left to right text, okay? So, that being said, let's jump to Swift now, the Swift part of this. How does Swift handle all of this? All right. So when Swift designers, like the great Gott Seelatner, designed string, they had a few goals in mind. One of the goals was obviously to honor standards like Unicode. And what they also wanted to honor was people usually don't think of strings in terms of Unicode. People will intuitively think of strings in ASCII terms. And they should be given reasonably correct results. Same thing applies both ways. And it should be hard to use incorrectly, and it should be easy to use correctly. And it should, by right, perform near optimal efficiency for 99% of use cases. let's see if they fulfill these goals. Well, firstly, Swift strings are Unicode aware, which is great. So here's an example, similar to an example I mentioned earlier. Let's say I have a string, cafe, and over here I use the accent Unicode independently. And here I use the other Unicode point with E with the accent directly. And if I compare both of them, they will be true. So one thing to note here is you can imagine that this is an expensive process. So we're probably paying a penalty for this, and I'm going to get to the penalty later on. But the nice thing is it'll work correctly. If you do this in many other languages like Ruby or Python, you'll actually get pretty funny results. I encourage you to try it. So yeah, string comparisons will always be performed using the Unicode canonical representation. And this is obtained after normalization, which I mentioned earlier. The other thing about strings is that they are value types. They follow value semantics. And so the nice thing here is that they will not be modified behind your back. Someone will not modify the reference to the string, and then when you get it, you'll be like, oh shit, how did this come here? The other thing is, interesting thing is that string is actually implemented in the standard library using a struct, which gives it all the nice reference semantics, and we can have both mutable and immutable versions of strings through Latin var. Okay, one thing obviously is strings are composed of characters. And this is where it gets interesting. This is why a character actually represents a grapheme cluster, which you should now be aware of at least. And if you don't want to use grapheme clusters, strings allow you to view what they look like in other representations as well. And this makes handling strings quite explicit. They don't hide this as an implementation detail, but they expose this for you. That is why you have all these things that's why you have all these views on a string. So you have the string.characters, which is the list of the grapheme clusters. You have the Unicode scalars, which are actually the code points, which I mentioned. And you have UTF-8, UTF-16, and UTF-32 encodings as well. So if you want to use those. So, performance. Okay, so we talk about performance. We're obviously going to pay some price for all these nice features, right? But in order to improve performance, string will actually use this thing called copy on write to minimize allocations of your string buffers. So how does that work? The way it works is that your string buffer on the heap is actually shared across different copies of the string. And it will actually be copied lazily upon mutation. So I'm going to show an example of how that works. Let's say I have this string, right? Let A equal iOS conf and var b is equal to A. How does it look like on the stack and the heap? On the stack, we basically have two values on the stack. Both of these are string, and they both point to a string buffer that is allocated on the heap. Okay? So every time you create a new copy, you're not actually creating a new buffer on the heap. It's actually, there's no buffer, there's no heap allocation happening. You're just adding a new pointer to the stack, which is quite cheap. So copying is actually quite cheap for strings. However, if you mutate this string, the moment you mutate it, let's say you call an append method, that is when the heap buffer will be copied, and that is when you'll actually allocate some more memory. And that is why if you do a mutation, the first in any sequence of mutation operations will actually cost you ON. Because of this behavior. This copy on write behavior, Swift actually does the same thing for all the other collection types as well, like array, set, etc. The other thing is handling substrings. So a very common operation is for you to slice strings, right? You want to get a subset of the string. And the way Swift makes it efficient is usually it'll return to you something called a substring, not a string. And you might wonder, why is that so? That seems a bit strange. The reason for that is substrings will actually share storage with the original string. So they will provide the same interface as strings, so you can actually perform all your string operations on them. But the copying of the string buffer is not going to happen. So you can efficiently use several substrings, and they will all share storage with the main string. However, obviously that comes with the caveat that you should not use substrings for longer than you need them. Because if you do, you're going to result in a very interesting memory leak. because substrings will actually hold a reference to the entire storage of the string. All right, so here's some performance, big O performance analytics for like some common operations on string. And some of the things I want to highlight here are things that you might not expect. For example, counting characters is ON, not O1, unlike several other string implementations. And this is primarily because of grapheme clustering. Like I mentioned, it needs to do all the Unicode normalization work, and that's why counting is actually a bit expensive. Operations like append are actually O1 amortized because string buffers will use some exponential growth strategy, so adding buffers is quite cheap. Indexing a string, once again, is also ON because, once again, of grapheme clustering. Copying strings are O1 because of copy on write, and slicing is also O1 because of substrings. So, however, Swift actually implements several other optimizations, so the big O numbers I mentioned actually might not apply for your use case, because if your string is based on ASCII, the implementation has several optimizations for only ASCII strings. Under the hood, they will actually separate the buffers for ASCII and non-ASCII strings. For non-ASCII strings, they'll use a UTF-16 buffer. For ASCII strings, they use a separate buffer. And they have several fast code paths if your string is just an ASCII string. And for small, very small strings, they won't even allocate memory on the heap. So this will help you save a lot of memory. All right, so finally, after that lecture, conclusions. First conclusion is strings are complex, okay? I hope you guys can appreciate that. They are not the easy, simple data type that you learn in Computer Science 101. Oh, they're so simple. They're just an array of bytes. No, they're not. They're very, very complex. You should never implement them yourself. You should never access strings or raw string bytes yourself. And Swift does provide you a safe string API. It's one of the first few programming languages to do so, along with Rust. But there are obviously some performance drawbacks. And naturally, if you are going to use string operations, especially with the character view, you have to be careful about these drawbacks. If you want performance, I would recommend you to use the UTF-8 or UTF-16 views so that you can optimize your code for like encoding or something. So that's it. That's all I got. Any questions, feel free to ask.